Hello, students. Now we'll start work and energy lecture 2. And in this lecture 2, we'll study work energy theorem and potential energy. So in the lecture 1, we have studied kinetic energy, what is work, what is energy, and energy is the ability to do the work. And work, that means if you are applying some force and towards this force, if you have some displacement, then you are doing the work, right? So now we will study work energy theorem. After that, we'll study potential energy. Okay, let's start. Now, the work energy, just a minute, I have to write, so I'm taking pen. The work energy theorem states that the net work done by a moving body can be calculated by finding the change in kinetic energy, right? That means the net work done, whatever the work, the body, moving body or the object it has done, that can be calculated by finding the change in kinetic energy. So we can write down the net work done, that is the W net, okay, that is the W net, that is the kinetic energy final minus kinetic energy initial, right? This is the difference in the energy. So here we can write down, and kinetic energy, we know that this is half m, just a minute, it will confuse you. So I'm just removing this one, again I will write. So half into m into velocity square. So I can write down Ke final, that is the half into m into final velocity square, and that means half into m into, suppose final velocity is v, so v square, and Ke initial, that equal to half into m into initial velocity square. So it will be half into m into initial velocity, suppose u, so u square. That means net work done, W net, that is the half final velocity, that is m v square minus half m u square. So I can write down that is half m v square minus u square. Okay, got the point? So energy work energy theorem, it states that net work done by a moving a body, that will be calculated by the change in kinetic energy. Fine. Okay. Now you can take that snapshot of this one, screenshot of this one. Let's move to the next slide. Now the net work done on a body is equal to change in kinetic energy of the body, that we know, and this is known as the work energy theorem. So it can be represented as K final, kinetic energy final, kinetic energy initial, that equal to work done, where Kf, this is the final kinetic energy, and Ki, this is the initial kinetic energy, and W is the work done, but it is net work done. Okay, or I can write net work done. Okay, fine. Let's move to the next slide. So the equation follows the law of conservation of energy, according to which we can only transfer the energy from one to another. I am doing the work, so that means the energy will be transferred to work, or if I am doing some work, that means I am getting the energy to do the work by some other means, like gravity, friction, external force, like this. If I'm applying external force, I'm getting energy, I'm doing work, right? So this is the main thing. So suppose you are here, and suppose you are here and you are just falling one object downward. So gravitational force will be acting here, right? That means this gravitational force, due to this, if the gravitational force, the gravitational acceleration is working here, so it will work. That means I can say that it will do some work, right? Suppose I have one object here on this surface, and I'm applying a force, external force. So due to this external force, the object may move towards this direction. So that means this is the external force, which is the main thing. What, due to which is the main thing, the object will move, right? So these are the examples. Now, according to work energy theorem, the work done by all the forces that equal to change in kinetic energy. So here Wg, Wn plus Wf, that equals to Kf minus Ki, where Wg is the work done by gravity, Wn, that is the work done by a normal force, and Wf, this is the work done by friction, and Kf, this is the final kinetic energy, and Ki, this is the initial kinetic energy. Initial kinetic energy. So if you have one object here, it may be this type or it may be ball. If it is falling downward, at that time there will be Wg is acting, that means work done by gravity, Wn, that is the normal force, and frictional force also there. So that equals to Kf minus Ki. That is the final kinetic energy minus the initial kinetic energy. Now work done by a constant force. So a constant force will produce a constant acceleration, right? Now let the acceleration is denoted by A. So A is the acceleration. Now from equation of motion, we can write down V square equals to U square minus plus twice AS, where V is the final velocity, U is the initial velocity, A is the acceleration, S is the distance, right? So that means twice AS, that equals to V square minus U square. Okay. So if we multiply, sorry, just a minute. If we multiply M in both sides of equation 2, let it be equation 2, let it be equation 1, so equation 2, then we will get, that is our M into A into S, that equals to M into V square minus U square divided by 2, right? So where S is the displacement of the body. Now here comparing the equation, if we now compare the equation, compare the above equation, we get that work done by force F, work done, that is the F dot S, F into S, and where that is mv square minus u square by 2, right? Because I'm explaining here, F into S, that equals to F is the what? MA into S. So MAS, this is the left hand side of equation number 3. This is the left hand side of the equation number, left hand side of equation number 3. Okay, so here we can write down that W, that is the MAS, or that equals to mv square minus u square by 2. That means I can write down work done, that equals to our m into v square minus u square by 2. Okay, fine. Now the equation W equals to F into ds, this is only valid when the force remains constant throughout the displacement. If the force that is changing, if the force is changing, at that time this equation will not be applicable. So this is only applicable when you have non-uniform force. No non-uniform force will be here, only uniform force will be here. Only uniform force. That means throughout the displacement, if the body is moving here, so this is the displacement. So whatever the force you are applying to the body, this force is constant. This force is constant. That means a particular force. If you are applying particular force here, that means whenever it will be displaced here, at that object also, you are applying the same force. So it is applicable, whatever W is the F into S or F into D, whatever you are calling, that is applicable only for the constant force. That means the force should be constant, remains constant throughout the displacement. Now, suppose we have a force represented below. Here, this is the curve where Fx is the force and this is the x, the displacement. And here we have xi and xf, where xf, this is the final position or final position of the displacement, and xi, this is the initial position or of the displacement. So here we can write W equal to integration of xi to xf, limit this one, fx into tx. Okay, and the x, that will vary from xi to xf. Okay, that will vary from xi to xf. Now the factors affecting the kinetic energy. As you know that the kinetic energy, that depends on the mass, it depends on the velocity, also it depends on the momentum and potential energy. So here energy can get stored in an object when work is done on it. So stretching a rubber string, the energy that is possessed by the body by virtue of its configuration or change in position is known as potential energy. We'll describe this thing, potential energy, very well, but later. Now, these are the three types of potential energy: gravitational, chemical, and elastic. So gravitational energy potential that comes from an object's height and weight. Suppose you have one object here at this height and this is the ground. So it has some potential energy. It has some potential energy. And this potential energy we will represent in this lectures, that is P dot E dot. Like kinetic energy, we have mentioned K dot E dot. Now potential energy we will express in terms of P dot E dot. Okay, got the point? Now the chemical energy. Now energy potential comes from the atoms. It contains and the chemical reactions that take place within the object. This is the chemical energy. Elastic, energy potential an object being compressed or stretched. That you are doing. Who are this? Who is this? This is your friend. So he is just stretching one rubber band. So you can see that the energy potential, an object being compressed or stretched, that time also we have some potential energy. So there are three types of potential energy. First one is the gravitational. Second one is the chemical. Third one is the elastic. Okay. Okay, fine. Next, when potential energy of an object at a height, that means you have some height here. So here, this is the H final, this is the H initial. It can move from here to here, or it can move from this position to this position, right? And we know that the work done, that is the force into displacement. And also force is the mass into acceleration. Now, whenever increasing height, then F equals to the force is the mg. Whenever increasing the height. So, the work done due to potential energy, that is the mg into h, because h is the displacement now. And mg is the force now. So work done due, that is potential energy, that is the mgh. And where the potential energy, the change in the potential energy, that equals to mg into h final minus h initial. Okay, got the point? So this is the potential energy. So what is potential energy? mgh. And what is kinetic energy? So kinetic energy is the half mv square, and potential energy, that is the mgh. Okay, if h is the height, g is the gravitational acceleration. Generally it is 9.8 meter per second square, and m is the mass of the body or mass of the object. Clear? Okay. Next. Okay. Now, law of conservation of energy. This states the energy can neither be created nor destroyed, but can be transferred from one form to another. The total energy before and after transmission should be constant. So what we have studied in energy conservation, law of energy conservation, the energy can neither be created nor destroyed. Only it can transfer from one form to the another form. Mechanical energy can be transferred to the sound energy, or electric energy. Electric energy can be transferred to the mechanical energy, but energy can be transferred from one form to another, but it cannot be destroyed or it cannot be created. So this term is very important. Energy can here this point is very important. Energy can neither be created nor destroyed. Please remember this thing. Only it can be, but can be transferred, from one form. This is FORM, okay? One form to another. Please remember this thing. Now you will tell that, ma'am, the eyes are small, one is small, one is big. Yes. Okay, fine. So energy can neither be created nor destroyed, but can be transferred from one form to another. This is the law of conservation of energy. Law of conservation of energy. Fine. Now the total energy, that is the kinetic energy plus potential energy. Now what is kinetic energy? Already we know that the kinetic energy is the half mv square. And what is potential energy? That is nothing but m into g into h. M into g into h. So this will be constant, right? Now by this time it is about to hit a ground. It has a velocity and therefore kinetic energy is half mv square. The energy gets transferred from potential energy to kinetic energy. Suppose the object is this at this height, so potential energy, that is mgh, and this potential energy, whenever the object that will fall at that time, this potential energy will be converted into kinetic energy, that is half mv square. That means the energy gets transferred from potential energy to kinetic energy, while the total energy remains same. The mgh plus half mv square, that is constant. That is constant. Okay, got the point? Now the potential energy. Now let's do some activity. So many things we have studied. Now let's do some activity. Suppose one rubber band. Yes, you go to your mother and just ask her to give you this rubber band. Now hold it at one end and pull from other. Pull. But don't leave one end. Okay, no, one side. So at that time it will hurt you. So the band stretches and release the band at one of the end now, but slowly. But please do it slowly, otherwise it will hit you with a very great force. So now what happens? The band will tend to regain its original length. So the band had acquired the energy in its stretched position. Now how it acquired the energy when it is stretched? That is a big question. Please think about this. Another activity, all of us, you have seen this thing, very interesting. Or take one slinky and ask a friend to hold one of its ends and you hold the other end and move away from your friend. Okay, you just move away, move away. Now you release that. What happened? You can see that the slinky acquired the energy when it is stretched, and would the slinky acquire energy when it is compressed, right? So that is also one activity, that of the potential energy. Now this is a toy car. In your childhood you have used this one, and this is the key of the car. Key of the car. And there was one spring inside this one. What we are just wind up this spring using this key. So first take a toy car, then wind it using its key, place the car on the ground. Now you just leave it, so you can see that it will move. So where did it acquire the energy? It acquires the energy because you have winded, due to the windings, number of windings, it acquired the energy, right? So that means one energy has been transformed into another energy, another type of energy. Fine. Now lift an object. Next activity, lift an object through a certain height. Okay, this is the ground position, this is the a little bit higher position, and this one is the little bit another higher position. Okay, so here you can see that the object can now do work. It begins to fall when released. Just you drop it, you just remove your hand, then it will fall. So it implies that whenever you have lifted, it acquires some energy, and if it is raised to a greater height, it can do more work, hence possesses more energy. So from where it will get the energy? That is a great question, right? So it will just get the energy because you have lifted it. And the potential energy, whenever it is released, the potential energy will be converted into kinetic energy. Okay, so the energy transfer to the spring inside is stored as potential energy for the toy car, and the potential energy possessed by the object in the energy present in it by virtue of its position and configuration. That is for the previous case, the man who is lifting this case. Okay, this for this case. Okay, now another activity, please do it. This activity, take one bamboo stick, make the bow, this type of bow. Now place an arrow here made up of light stick, and then stretch this one, this string, and release the arrow. It will fly off the bow. Notice the change in the shape of the bow. At that time, you can see that it will be like this. So this much is the stretch condition after flying of the bow. This is the condition. So the potential energy stored in the bow due to change of shape is thus used in the form of kinetic energy in throwing of the air. That means the potential energy that has been transformed to the kinetic energy here. Okay. So an object increases its energy. An object increases its energy when raised through a height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is the gravitational potential energy. The gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground. Okay. So energy is required for the evolution of life forms on the earth. In physics, it is defined as the capacity to do work. We know that energy exists in different forms in our nature. Now, what is law of conservation of energy? Just now we have studied, just for brush up I have given again. Energy can neither be created nor destroyed, only it can be transformed from one form to another form. Okay, so this is very, very important. Please remember this one. This question, write down the law of conservation of energy. This is very much required. Please remember this thing. And here in a closed system, a system that is isolated from its surroundings, the total energy of the system is conserved. This is the conservation of energy. Now here you can see that whenever the apple that is at this height, it has potential energy. Whenever it will fall at that time, this mgh, where h is this much distance, this will be converted to half mv square. And here mechanical energy, that is converted, the mechanical energy here. Now, so isolated systems such as the universe, if there is a loss of energy in the some part of it, there must be gain of equal amount of energy in some other part of the universe, because it has to maintain the law of conservation of energy. So if there is some loss at some part, then at other part there should be some gain of energy. So here this is very, very important. That's why the energy has been conserved here. Now the amount of energy in the system, you can see that is determined by the following equation. I am writing the equation ut, that equals to ui plus w plus q, where ut, that is the total energy of the system, total energy of system, ui, that is initial energy of the system, initial energy of system, and q, this is the heat added or removed from the system, and W, this is the work done by or on the system. Okay, and the change in the internal energy of the system is determined by the equation that is delta U, that equals to W plus Q. Just a minute. The pen is not listening to me. That is the main problem. Okay, fine. So this will be Q. Okay, and this UT, that equals to UI plus W divided plus Q. Okay. So law of conservation of energy derivation. Now we'll do this derivation, and this derivation is very, very important. The energy, that is the mgh, where h is the height of the fruit and the ground, right? So E equals to mgh. Now the potential energy, here the energy is the how much it is constant, and that is kinetic energy plus potential energy. So potential energy is the mg into x, or x here we can find out this is nothing but, or that is the height or the distance between the apple and the ground, distance between the apple and the ground. Okay. So according to third equation, according to third equation, here v square, just a minute, according to third equation, v square, that equals to twice g h minus x. Okay, and that equals to, it implies that half mv square, so that will be half into m into twice g h minus x. So kinetic energy, that is the half into m into twice g h minus x. That means this 2 will be cancelled. So kinetic energy, that equals to m into g h minus x. Now the kinetic energy, that equals to mg h minus x, right? Potential energy. So this is equation number 3. Now using equation 1, 2 and 3, E equals to mg h minus x plus mgx, that equals to mg, if I take common mg, h minus x plus x, so this will be mgh, right? That means our energy, that equals to mgh. Okay, fine. So here, now similarly, if we see the energy at point C, which is at the bottom of the tree, suppose this is the C point, and it will come out to be mgh, and this is the point where you have the difference x, and this is the total height, that is the h. Okay, so Here we can see the fruit is falling to the bottom, and here potential energy is getting converted to kinetic energy. So there must be a point where kinetic energy becomes equal to the potential energy. And if we assume that this x point, this x height is the height, we need to find the height of x from the ground, then we have to apply this derivation. So at x, as the body is at height x from the ground, I'm drawing it, this thing. This is the ground. Suppose this one is the x, and at that time, so I have written some equations here. Okay. Now at that time, if PE, potential energy, that is the mg into x, let it be equation number 5. So kinetic energy, that equals to potential energy. That means potential energy that equals to kinetic energy, that equals to E divided by 2, right? As the body is at height x from ground, so potential energy that equals to mg into x. Okay, let it be equation number 5. Sorry, this is equation number 4. So this will be your equation number 4 again. No need to give the equation number here. Now, so mgx that equals to mgh divided by 2. So x equals to h by 2, where h by 2 is referred to as the new height. As the new height. Okay. Got the point? Now the energy conservation. Here, energy conservation is not about limiting the use of resources which will finally run out together. So here the idea is that to conserve the energy. That means reducing the demand on a limited supply and enabling that supply to begin and rebuild it. That is the energy conservation. So we have to conserve the energy. As you know that the fuel energy and all other energy that will be exhausted soon. So that's why we are just trying to search other source of energy, or we are trying to conserve the energy whatever we have in our hand. So law of conservation of energy example here. Now in physics, most of the inventions rely on the fact that energy is conserved and it is transferred from one form to another. A number of electrical and mechanical devices operate solely on the law of conservation of energy. I am giving some fuel, so it will be converted into the mechanical energy, the car is moving. Or some electric car, at that time the electrical energy that will be converted into the mechanical energy. In a torch, chemical energy of the battery that is converted into electrical energy, which is converted into light and heat energy, right? So the law of conservation of energy we are using a lot in our daily life. In hydroelectric power plant, hydroelectric means from water, speed of the water, you are just getting the electricity. So hydroelectric power plant, water falls on the turbines from a height, and then the turbines will rotate and it will generate the electricity. So we are converting the waterfalls, whatever the energy in the waterfalls, that we are converting into the electricity, right? Another thing, potential energy of the water is converted into kinetic energy of the turbine and converted into electrical energy. In loudspeaker, what you are doing? Electrical supply you are giving, but what you are listening, that is sound. So in loudspeaker, electrical energy is converted into sound energy. Microphone, I want to say something, and I'm using microphone now. So microphone, what it will do? It will just convert my voice. That means what? The sound energy converted into electrical energy. Sound energy that will be converted into electrical energy. Okay. And so many other examples are there. In generator, you are just applying what? You are applying some diesels. So the mechanical energy is converted into electrical energy. When fuels are burned, chemical energy is converted into heat and light. Chemical energy from food is converted to thermal energy when it is broken down in the body and is used to keep us warm. Okay, this is the most favorable example that always we have in our body. We are taking the food, that food will be converted into thermal energy, and like your ATP, right? It will generate some ATP. So it is broken down in the body and then it will keep our body warm. Keep our body warm. Okay. Now the power. The power, this is the rate of doing work or the rate of transfer of energy is called the power, and it is denoted by P, where work divided by T, right? W divided by T. The rate of doing work or the rate of transfer of energy is called the power, where W is the work done and T is the time. Okay, and SI unit is the watt. SI unit is the watt or joule per second And average power is what? Total energy consumed by total time taken. And commercial unit of power, that is kilowatt hour. Kilowatt hour. Now one thing I want to tell you, kilo, that means 1000, and hour, this is 60 into 60, that is 3600 second. 3600 second. So using this 1 kilowatt hour, that we can write down, that is 3.6 into 10 to the power 6 joule. Please remember this thing. Or otherwise, no need to remember this thing. 1 kilowatt means what? 1000. Kilowatt per hour, that means 1000 here. And you have what? That 3 kilowatt into hour. Hour is the what? 3600. So it is 3.6 into 10 to the power 6. I'm just describing here. I think that you are not understanding. So 1 kilowatt hour, that is 1000 into 3600 watt second, right? So this will be 3.6 into 10 to the power 6. Here you have 3, here you have 2, 5. So if 3.6, then it will be 10 to the power 6 watt second. And that is called 3.6 into 10 to the power 6 joule. Now it is clear, I think. Okay. Thank you. Till now, I think all of you understood. If you have any confusion, you can ask me.